next talk and the second last talk of the conference will be given by Vsevolod Gubarev. Vsevolod, are you here?
Yeah, hello to everyone.
Can you please share your slides?
Yes.
Sorry, it's my dog. So Vsevolod works in Sobolev Institute of Mathematics, and today he is going to speak about Rota-Baxter groups and braces. You can start.
Okay, thank you. I want to thank organizers for the possibility to give a talk. And of course, I start with congratulations to the anniversary of both Valeriy Bardakov and Andrei Vesnin. And my talk is devoted to the results from two joint papers with Valeriy Bardakov. And it's a brief plan of my talk. And I don't want to go to all details because of the time restrictions, but okay, my general goal is to show in general, to say something about the results, about the context from which they originate. Okay, I start with Rota-Baxter operators on algebras. It's not so a new object. It was defined by Glenn Baxter more than 60 years ago. And okay, here we deal with any kind of algebra, not necessarily associative, not necessarily one. And here we also involve some scalar from the ground field. All algebras will be defined over fields. And the scalar kappa is called a weight of Rota-Baxter operator. And you can look at this identity as an algebraic generalization of integration by parts formula. And there is okay, short history of the subject given below at the bottom. And it's important to highlight that in 80s, Valeriy Drinted and Semenov Tenchansky, they rediscovered this notion in terms of classical Yang-Baxter equation. And more than 10 years ago, the first monograph on the subject was published by Li Kuo. Okay, let me give some examples. And historically, one of the first examples given by Glenn Baxter, it's just nothing more than integral operator on the algebra of continuous functions with point-wise addition and multiplication. And it's a Rota-Baxter operator of weight 0. Further, we may consider something close, but here we deal with any kind of field. In example 2, okay, of course, it's a field of characteristic 0. And formal integration on the polynomial algebra is again a Rota-Baxter operator of weight 0. If we have invertible derivation on an algebra A, then its formal inverse is again a Rota-Baxter operator of weight 0. For non-zero weight case, a canonical example is comes from a decomposition of an algebra into a direct vector space sum of two subalgebras. For example, you may consider the factorization of the decomposition of the matrix algebra into a direct vector space sum of non-strictly upper triangular and strictly lower triangle matrices. And okay, it's an example of if you project everything on one of them with some, okay, maybe rescaling with some scalar, then we will get a Rota-Baxter operator of non-zero weight. Okay, there are a lot of known connections of Rota-Baxter operators on algebras, but I want, it's important for my talk, only to say about two of them. The first one is devoted to induced algebraic structures. If we have, and here, okay, I concentrate only on the algebras. If we have a Lie Rota-Baxter algebra, so it's a Lie algebra, and do it with a Rota-Baxter operator of weight 0. Then firstly, we may define new dot product, and it's known to be left symmetric or sometimes called pre-Lie one. And also with the help of this dot product, we may define new Lie product on the same space A. And okay, just very short comment that left symmetric algebras also very important for geometry, for category theory, for vertex algebras, and so on. Okay, it's out of my interest for this talk, but okay, itself is an interesting object. If we preserve, okay, if we start with Rota-Baxter operator of weight 1 and preserve the initial product, we will get so-called post-Lie algebra. Okay, I avoid the details, but okay, there is some list of identities in terms of these two operations: dot product and curly bracket product. And okay, theorem 1, it works in general, but okay, I formulated in the context of Lie algebras. Pavel Kolesnikov and me proved 10 years ago that we may injectively embed any pre-Lie or post-Lie algebra into corresponding enveloping Lie Rota-Baxter algebra. And like an analog of Poincaré-Birgeau theorem in this context, in 2019, I have constructed exactly universal enveloping Rota-Baxter algebras. Okay, the second application or connection, maybe the most important one, is direction of Yang-Baxter equation. But here, to the moment, we deal with so-called classical Yang-Baxter equation, which can be considered as a limit of quantum Yang-Baxter equation, or solution of quantum Yang-Baxter equation. And if we consider it over some semi-simple finite dimensional Lie algebra over a good field, then Bellarmine and Rietveld noticed that we may get exactly Rota-Baxter operator of weight 0 with the help of good form. Okay, here we apply Killing form, which is always defined on such Lie algebra G. And only recently, similar result for weight 0 was obtained by Maxim Goncharov. So fixed here that, okay, we started with Rota-Baxter operators on algebras, and for us now it's important that we have two connections with some induced algebraic structures. It's the first direction. The second direction, connection with Yang-Baxter equation. Okay, now we go to so-called Rota-Baxter operators on groups, and we will try to consider something analogous in the context of groups. And this notion is very fresh. It was, the corresponding article was published less than 2 years ago. And motivation, here let me comment, we deal with any kind of group, not necessarily finite, not necessarily abelian, any kind of group. And here B is nothing more than map. Yeah, we don't say that it's homomorphism and something else. And there is an identity, and it's important to highlight here that this Rota-Baxter operator on a group is an analog of Rota-Baxter operator of weight 1 or of non-zero weight. And to the moment, there are no an analog or definition of Rota-Baxter operator of weight 0 on a group. Yeah, so it's interesting that here we deal with non-zero weight, and we may apply some intuition from Rota-Baxter operators of non-zero weight defined on an algebra. The most important motivation for authors was to go through the known correspondence between Lie groups and Lie algebras, and corresponding to such defined map linear operator on the Lie algebra is exactly Rota-Baxter operator of weight 1. Okay, it's like an analog of one of our examples. If we have some invertible one cocycle, then its formal inverse is a Rota-Baxter operator on the group G. And as above, we may consider some induced algebraic structure. It's a circle product defined by the formula 2. Okay, let me list down some properties of such maps. Okay, E denotes here the unit of a group G. It's preserved by any Rota-Baxter operator. If G is abelian, then B is nothing more than homomorphism. Image and kernel of such maps are always subgroups, but not necessarily normal ones. And always we have so-called trivial Rota-Baxter operators, B0 and B minus 1. We have an inversion on the set of Rota-Baxter operators, B tilde. And if we interested on the classification results, like what is the full list of Rota-Baxter operators on a given group, for example, finite group, it's important to apply conjugation with automorphism of this group, because they preserve more or less all algebraic properties. Okay, not so easy properties, more thin properties given by Ligo and co-authors. And this list of 4 properties is exactly an analog of the same results stated by Semyonov-Tenchansky 40 years ago for Lie Rota-Baxter algebras of non-zero weight. And here, if we involve now circle product, then kernel of B, or of this corresponding B plus, both are normal subgroups in GB. We have an isomorphism of corresponding quotients, and we also, it's important, we always have a factorization of a group G into a product of 2 subgroups. And here it's like an analog of splitting Rota-Baxter operator. It's important here. It's important that the order is exactly how it's written, because initial group may be not abelian one, and we inverse the second multiplier, to get Rota-Baxter operator on G. And not a difficult result. There is some kind of criterion how to check that given Rota-Baxter operator is exactly a splitting one. More interesting result, how to extend a given Rota-Baxter operator from the second, from the middle subgroup of G, and we have some kind of triple factorization with some restrictions. Then we may extend it by the given formula, and it works. And just color which works for 2-step nilpotent group, for example, Heisenberg one. It provides some example of Rota-Baxter operator on such group G. Lemma 4 was stated in several works. Just if we consider a homomorphism from the whole group to its abelian subgroup, or just anti-homomorphism, then we always get a Rota-Baxter operator. Example 5 is a particular case from the more general construction given in theorem 2. Here it's interesting that we start with Rota-Baxter operator of wave 1 on an algebra. It's a direct sum of n copies of the ground field. it's known, okay, there is a more or less complete classification, description of such operators. There is only a finite number of such ones. And it's not a restriction. We may assume that corresponding matrix is upper triangular, and moreover, it consists only of its coefficients are only 0 or plus minus 1. That's why we may consider the following formula for Ti. It's correct. And if we collect all such Ti's in the tuple, then we will get an example of Rota-Baxter operators. And example 5 is just a particular application of such construction. Okay, another known correspondence between groups and Lie, not algebras, but Lie rings, comes from not the correspondence between Lie groups and Lie algebras, but from the lower central series. And if we consider formal direct sum of the corresponding quotients, we may get a Lie product of Lie ring with the help of commutator, is group commutator defined in group G. And we may extend Rota-Baxter operator from a group G to this Lie ring LG, and it will be exactly of weight 1 if if we preserve these quotients unit works. There are some also examples how it works, but okay, I have to go further. And now, today we heard about braces, skew braces, but okay, unfortunately it was given an opposite definition for right one, but okay, it's the same. We just have to invert all products and nothing more. It's exactly the same notion, but written from another side. As it was said, it was defined by Guarneri and Vendramin in 2017. It's a more general notion as so-called left brace, defined earlier by Wolfgang Trump, because here we have no restriction that dot product group is abelian one. But in both articles, the main goal was to describe, to give some solutions to the set theoretical solution to the quantum Yang-Baxter equation. However, we may find such more or less equivalent definition of left brace coming from radical rings in the lectures of Kurush more than 50 years ago. And not very difficult to prove, but one of the most interesting results of my talk, that Valeriy Georgich and me, independently, but Valeriy Georgich did it earlier, noticed that if we start with Rota-Baxter group, okay, we know that the circle product is also another group product on the same set G, but it's important that we have this, okay, let me return. We have the third identity fulfilled, this some kind of compatibility, and it holds. That's why starting with Rota-Baxter group, we always may induce a skew left brace structure on the same set G. And okay, mentioned today, interesting article published this year, devoted to some generalization to multi-braces or to brace systems, and also some kind of this result works for them too. Okay, if we consider trivial Rota-Baxter operators, not surprisingly, we will get as outcome, we will get trivial skew-left braces, just with the same product or with the opposite one. If we start with splitting Rota-Baxter operator, we will get very famous and noted by several authors skew-left brace, with this product written at the bottom. Further results devoted, like an analog of the results which was proven by Pavel Kolesnikov and me, and very close construction, we may embed every skew-left brace into corresponding Rota-Baxter group. It's an open question how looks an universal envelope in Rota-Baxter group. It's an open question. Although we know, it's references given, we know how looks free Rota-Baxter group. It's not very difficult construction, And we theoretically know that inside this free Rota-Baxter group, we may consider corresponding terms, and we have to get free skew-left brace. Technically it looks not so easy, and also it's another open question, a construction of free skew-left brace. It's an open question. In general, not every skew-left brace comes from some Rota-Baxter operator, but under some conditions, which are listed here, if we know that a group has trivial center and it has only inner automorphisms, then we get all skew-left braces structures originate from Rota-Baxter operators. Below there is a list of 3 articles which in some sense extend or continuing on this and previous results. Firstly, Carenti and Stefanella characterize exactly in terms of cohomologies when given skew-left brace structures come from Rota-Baxter operators and when not. Catino, Mazzotta, and Stefanelli extend these results in the context of Clifford semigroups, and something close to semigroups was considered by Lee and Wang in their also articles devoted to Rota-Baxter systems and skewed trusses. Let me return to the construction devoted to the product of the same group G and Rota-Baxter operators on a direct sum of n copies of a field. It's an interesting article. It's a series of articles, and I give only reference to one of them by Sidney Tsang, and he was interested how to compute the number of the isomorphism classes of skew-left braces with isomorphic both dot and circle products and product groups, and both are isomorphic to the nth power of some fixed finite non-abelian simple group. It's an interesting that the answer doesn't depend on the choice of G, and up to the first except the first term in this sequence, we surprisingly get the number of orbits of Rota-Baxter operators up to conjugation of weight 1 on the sum of n copies of a field of the ground field K. And I slightly generalize the construction which was given above, and I involve here also n-1 automorphisms of the group G, and then it's a question or some kind of conjecture that maybe all such isomorphism classes of skew-left braces with the conditions which are listed at the top originate from exactly Rota-Baxter operators defined by the formula 4. It's an open and I think interesting question. And also, yeah, I should mention that this question of Zhang originate not only from the theory of skew-left braces, but also from so-called Hopf-Galois structures, which is known for several decades. And okay, this kind of questions are typical for this area. And okay, the final point of my talk, just an application of this new Rota-Baxter operators on groups to the solutions to the quantum Yang-Baxter equation. Okay, today we already have all kind of required definitions. And let me go to the main theorem from this subject. It's a new result, but in the core we applied the formula obtained by Guarneri and Van Rabin for skew-left braces, but we have rewritten it in terms of a Rota-Baxter operator. Okay, it looks nice. It's exactly lambda map which was mentioned by the morning section. And we will get non-degenerate solution, which is involutive if and only if the dot product is abelian. And this formula was also extended by Katina and co-authors for Clifford Rota-Baxter semigroups. Okay, let me finally mention this table, like more or less a context in which this investigation may be considered. So in the central column, we have some kind of Rota-Baxter algebras or algebraic structures. To the left, we have the list of induced algebraic structures, and to the right, we have some kind of Yang-Baxter equation. Okay, I didn't paste here also Hopf algebras, and there is something close in terms of Hopf algebras, but okay, let me keep it as it is. And still in this table there are several blank places about connections and so on, and it can be studied in the future, I hope. Okay, thank you for your attention.
Thank you, Vsevolod. Are there any questions from the audience?
Yeah, I have one generic question. So is there a recipe, more general recipe for constructing RB operators on a given group other than the exact splitting?
Sorry, can you repeat the beginning of your question?
So do we have other methods of constructing Rota-Baxter operators on a group?
Matter or what? Sorry.
Do you have a general method for constructing?
I don't know. Yeah, just if we go to more known subject like classification, if we are interested on the complete classification of Rota-Baxter operators on a given finite dimensional algebra, it's in general a hard problem. So I believe that here, just for general group, just finite group is also hard problem if we are interested to list down all of them.
Yeah,
but
up to equivalence, yeah.
Yeah, just up to conjugation with automorphism is still hard problem. But okay, I had some time restrictions, but in our articles with Valeriy Georgievich, there are several another constructions devoted to the subject, how we may construct such maps.
Yeah, you have constructed special constructions of Rota-Baxter operations for groups which satisfy specific conditions, like split, which can be split,
Exact
decomposed.
split,
Yeah, but I can return that it's a conjecture that, okay, in terms of this question of chunk, it's okay. We hope that with the help of such construction, we will get all required skew-left braces, for example. So there are some concrete constructions, but for some cases, they give maybe everything.
Thank you.
Uh,
Other,
Can I ask to Mahender? Because yes, Mahender, very good question. But we have in some sense full descriptions of Rota-Baxter operators only for abelian groups. Because for abelian groups, Rota-Baxter operator is a homomorphism. But if you consider the two-step nilpotent groups, when it's problem to describe all Rota-Baxter operators, I started to do something. It's need to finish with calculations. And also interesting problem to describe all Rota-Baxter operators on a free group of rank 2. We still have found some type of operation, but operators, but the full description, I think, difficult problem. Yes.
Okay, thank you.
will
Also,
it
like
give,
given like semi-direct products or some kind of decomposition, how to extend Rota-Baxter operator from one component to the full group or something like that.
Yeah. There are some constructions given by us for semi-direct products, for rest product, yeah, and so on. But okay, in general, they do not give all of such operators.
Thank you very much.
can I please ask a question about
Yeah.
connections between Rota-Baxter operators on groups and skew braces? So is it true that if I classify all Rota-Baxter operations on a free group, for example, with two generators, then I describe all the possible skew braces with the multiplicative group, which is free group?
No, it doesn't work because not every skew-left brace originates from Rota-Baxter operator.
I thought
Every
that,
Rota-Baxter map gives some skew-left brace, but not every skew-left brace. Okay, if we return to the theorem 3, just inside your Rota-Baxter group, there are all of such structures, but okay, as a subgroup, but okay, it's like some kind of, for example, you may consider as an analog of the Kelly theorem, yeah?
I see. Yeah, I didn't catch this moment that they're not in one-to-one correspondence, but there is an embedding.
Yeah.
So other questions? So if there are no more questions, I suggest to thank Vsevolod for his talk.
Yeah.